Good morning, good afternoon, and good evening, everyone. I see we have some attendees from across the globe today, which is wonderful. Thanks so much for joining me. My name is Shannon Holmes. I'm a medical physicist here at Standard Imaging, and I'm excited to be able to talk to you today about small field scanning. Standard Imaging believes that it is your time. Be precise. We are, of course, here to help you in any way that we can. A little housekeeping before I really get into the meat of the talk today. I am recording the webinar. So if you get interrupted, if you have to step out, or if you want to share it with a colleague, look at or watch your emails later today or tomorrow. You should get a link to the recording of the webinar. If you have questions at any time during my talk, please feel free to enter them in the GoToMeeting dialog box under the questions. I'll try and catch those as they come in. They do pop up on my screen briefly, but if I miss it, I will certainly circle back around to it at the end of the discussion. If you don't know who we are or aren't as familiar with us, Standard Imaging is based in Middleton, Wisconsin. We're just outside of the capital city of Madison. It was founded in 1989 with a modest suite of products, but has grown significantly since then so that we now design and manufacture a full suite of QA products for radiation therapy. So to the topic at hand, if we're talking about small fields, we need to define what we mean by small fields. So the AAPM and IAEA report TRS 483 defines small fields as meeting at least one of these three conditions, either loss of lateral CPE, charge particle equilibrium, on the beam axis, partial occlusion of the primary photon source by the collimating devices on the beam axis, or the size of your detector is similar to or large compared to the beam dimensions. So if we're talking detectors specifically first here, how do they impact your small field scanning measurements? Well, first and foremost, it's size. Of course, we're talking small fields, and oftentimes with a lot of the detectors that we have, when we get into small fields, we do meet that condition of the detector being comparable to the size of the field that we're measuring. So it affects not only the volume averaging, the size and the shape of your detector, but also obviously the shape affects the direction in which you're measuring the field if you're scanning with it. If you don't have a uniform detector both across and in line with the detector, then you're averaging differently when you scan in plane and cross plane. The size of the detector also affects how well you're determining that penumbra shape because of the integration that's done over the size of the detector. Positioning becomes a much bigger issue with small fields because a slight offset in positioning, particularly for something like output factors. With profiles, you can see the offset just a little bit more, but positioning is critical for small fields, of course. The second way that your detector affects your measurements is with perturbation of the beam. When you're putting something into your water tank to make these scanning measurements that is not water equivalent, you are changing the radiation interactions right there at the point where you're trying to measure them by replacing that water with your detector. Ion chambers, obviously less dense than water, will under-respond. Diodes, more dense than water, will tend to over-respond. So things to think about with the detectors that you're choosing. With your ion chamber, how big is your air cavity, especially when compared to the size of the field that you're measuring. With a diode, what is that density? How does that, how big a region is that higher density covering? Some diodes have built-in compensation. This is usually an air gap next to the higher density diode, trying to balance out that higher density region with an adjacent low density region. This can be good, this can be not so good, depending on your diode, how well it's characterized, and whether that compensation is designed for the energies at which you're using it. As you're measuring with a diode as well, the response can vary with energy because of either usually over response to low scattered photons, over response. And now I'm questioning myself to a change in response to those low scattered photons. And as you scan a PDD or as you scan out in your profiles, you need to be aware of that change in the spectrum, potentially changing the response of your detector. There are published corrections sometimes available for various detectors. There's an example plot here from Paulo Francescan, shows the under response of the ion chambers and even a liquid chamber requiring greater than unity corrections. Diodes, because of their over response, require less than unity corrections to account for those. The key on published corrections is to make sure that you're matching the conditions under which these were calculated or measured. They only really truly apply when the conditions match. Another thing to consider with your detectors is the signal level. So with ionization chambers, your signal is directly proportional to the collecting volume of your chamber. So as you decrease that volume, your signal decreases proportionally. So your signal to noise ratio becomes a little bit more of a concern. You need to have sufficiently sensitive electronics for those small signals as you get to really small chambers, as well as high quality triaxial cables. The diodes give you a larger signal, obviously, than the microionization chambers. So that is an advantage to the diodes on the signal to noise ratio. When concerning yourself then now with this fourth point of the signal to noise ratio, it is very important that you give your electrometer a proper warm-up. Those components within the electrometer need to come to a thermal equilibrium in order for the electronic noise within the system to be stable, so that your leakage is minimized and that you can zero out as much of that electronic noise as possible. You want to make sure that if you have a choice of ranges on your electrometer, your scanning electrometer, that you match the signal strength to the proper electrometer range. Some water tanks are auto range or just have a single range, but if there is a choice, you want to make sure that it's matched properly. The other thing that I put here, it matters a little bit more for your output factor measurements, because in those cases, you're more likely to be using a long cable that you maybe just unwound and ran through the raceway out to the control room. But there are some triaxial cable effects to be aware of, both within the cable from the chamber as well as your extension cables. One is, of course, cable-induced signal. As you irradiate it, you can create some charge through the Compton interactions with the metal within the cable. But there are also potentially some triboelectric effects. These are mechanical strain on the cable, especially if it's a tightly wound cable that you're just unwinding before you make a measurement. The relaxation of the physical components of the cable can cause a slight drift in the signal. So if your system's not holding at zero and you've had a long cable like that you just unwound, especially for output measurements where you have your electrometer outside the room, that is definitely something to consider. Best to unwind it. If you have to unwind and rewind your cable each time, don't wind it tightly. Unwind it as soon as you can to give it enough time for that physical relaxation before you make your measurements. Another category for how detectors impact measurements is the accuracy of your detector. Do they have energy dependence? Diodes can often have a low response out of field and thereby underestimate a large region of low dose in your stereotactic patients. Compensated diodes, once again, is that good or bad? It really depends on the situation and what you're looking to achieve with that diode, as well as how well characterized it is for the work that you want to do with it. Corrections for your measurements may be depth dependent because of those spectral changes, depending on just how sensitive your detector is to changes in the energy spectrum, as well as scatter conditions. Because once again, that can change the energy of the radiation that's interacting with your detector. Some detectors have angular dependence. If they do, I advise you to use it in the orientation for which it was designed. That's where it will behave best. or be aware of implications if you're trying to turn a diode on its side, or measure end on to an ionization chamber, that sort of thing. Be aware that there may be some implications of those. Dose rate or dose per pulse dependencies are also detector specific, and so they require understanding not only your detector and whether it has those dependencies, but also your accelerator and how the dose rate changes the dose per pulse. If it's just more doses, or excuse me, more pulses, but the same dose per pulse, then there's less dependency, particularly for ion chambers, than there is if the dose rate changes the amount of signal that's given in each of those dose pulses. So what's the best option? Considering all of those things, there's a lot to think about, obviously. But for small field scanning, we've got three main options for you. So there's the ionization chambers. The A26 is the microchamber that I'd recommend. The A28 I list here just because that's our standard scanning chamber, the 0.125 cc, but the A26 really is the small field detector. There's the diode. In our case, this would be the Exradin D1V scanning diode. Or there's the scintillation detector, the Exradin W2. Each of these detectors has both strengths and limitations, just like any detector that's out there. So your best solution as you're characterizing your small fields is a good combination of detectors. In this particular set of three, what I really like about it is you've got the water equivalent scintillator in the middle. And on the under response side, you've got the ionization chamber that's well known. On the over response side, you've got the diode, also fairly well known. If you apply the proper corrections to the ion chamber and the diode, they should meet in the middle where the scintillation detector is. And so that really does build your confidence in the measurements that you're making. So about these detectors, just a little bit more. The A26 was designed specifically in response to an investigation done at the UW-Madison about the behavior of microionization chambers, actually the lack of proper behavior of microionization chambers, particularly in regard to the polarity effect for these chambers. And so as a result of that investigation, we were able to develop the A26, considering several things specifically listed here. One is we wanted to make sure that we had a spherical spot size, spherical measuring volume, so that the orientation of the chamber within the field really didn't matter. Your volume averaging was going to be identical no matter which orientation you were using. We modeled the electric fields to verify that shape as we were designing the chamber. We looked at chamber volume, and in this case, because of the conducting plastics that this is made out of, we wanted to avoid the high Z materials of a wire or metallic components. So because of those plastics, we were trying to make it absolutely as small as this could be made, and still have a well-behaved ionization chamber. So we've got 0.015 cc volume for the A26. But if you look at spot size, the A16 is our smallest chamber at 007, but its spot size is 3.5 millimeters. This is smaller because of that wire in the middle. The A26 is almost double the volume, or just over double the volume, for less than a millimeter larger spot size, and that's the diameter across here, what we're calling spot size. So you're not losing much in your resolution, but you're doubling your signal from your chamber. So that helps with signal to noise as well. And we were definitely considering signal magnitude and SNR in the development of this chamber as well. So strengths of the ionization chambers, particularly the A26, is that it is a reference class ion chamber. Its spot size is independent of the orientation, and it's a familiar technology for most physicists. We're used to using ion chambers. We're used to troubleshooting when things aren't going quite right, and figuring out what might be going on with those chambers. Limitations of the ion chamber is that although it's as small as we can make it, I don't think you'll find a well-behaved ion chamber any smaller than this ever. We have very, very good processes. We've been doing this for a long time, and this really is the smallest you can reasonably make something like this. There is a small perturbation due to the air volume. It's not a perfect point. Ion chambers never are. The diode, the D1V, we actually have two configurations of our diode. It's the same diode in two different housings. So if you've heard of the D1H, that's this horizontal version. That's really meant for phantoms, but the vertical one, the D1V, is designed for scanning. And so it's held vertically in the beam in order to have a minimal perturbation in terms of the stem and the lateral scatter of the radiation within the water. It is an unshielded diode, has a 1 millimeter diameter spot size, so a nice small amount of volume averaging. And there are correction factors available for it. There are a couple of publications in 2014 that looked at both measured and calculated factors, such as this one from Papakonstantopoulos et al. So strengths, and here's a different one, another one from Paolo Franciscan. I think I showed some of his earlier work earlier as well. Strengths of the diode, again, it's a well-established technology. There's very minimal volume averaging. It has a low angular dependence. There is an angular dependence, so I wouldn't turn it on its side. But for scanning and on in a water tank, you won't have any issues with that. The limitations, as with any diode, is that it's not water equivalent. There was a question about the ion chambers. Which one would I recommend for measuring small field point dose, the A16 or the A26? I would actually recommend the A26 because of its design and because it was designed to be a reference class chamber. The A16 has a longer history, but it does have that metal electrode, and it suffers from the same sort of polarity effects that every other microionization chamber besides the A26 suffers from. The scintillation detector, the Exradin W2, is an organic scintillating material. We have a couple different configurations. There's a fiber that they're both 1 millimeter diameter, but we have 1 millimeter long and 3 millimeter long scintillators coupled to an optical transfer fiber. The prior version of this detector was the W1. That was available only in the 1x3. The rationale for keeping the 1x3 actually is, well, higher signal to noise because you're generating more signal. So for those fields where you want to scan a little bit faster or you want a little bit higher signal because you're suffering from that signal to noise issue, the 1x3 gives you that comparison with published values with the W1 as well as the higher signal for those slightly larger small field applications. When you really get down to the teeny tiny fields though, you really need the 1x1 in order to have the resolution, measurement resolution and limited volume averaging that you're looking for. The huge advantage of the scintillator is that it's water equivalent. This is all made out of organic. This is an organic scintillator and a PMMA optical transfer fiber. And so you're with this detector, you're not perturbing the dose right there at the point of measurement, which is huge when you're talking about your corrections. The difficulty with the scintillator is that it does require a correction for the Cherenkov light that is produced by those high energy electrons in that PMMA optical transfer fiber. So it manifests really as a stem effect sort of signal. The detector also is not an absolute dosimeter. It is something that degrades as it gets dose, just like your diodes do. If anybody has seen, well, most of you I'm sure have seen older PMMA phantoms that have been irradiated a lot, they start to turn yellow. That's the same thing that happens with this fiber. It ages under radiation. So you do need to recalibrate it or recharacterize it periodically with both what we call the Cherenkov light ratio or the CLR, as well as a dose conversion to convert the light signal to a known dose as it accumulates dose. The method that we use is actually a 2-channel chromatic correction published by Matthew Guyot et al. And so our scintillator is a blue scintillator, so that we get the scintillation peak here in the blue region. The Cherenkov light is a broad spectrum contaminant. And so the method that we use for this, outlined by this paper, has you do 2 measurements. You do a measurement, what we call a minimum fiber measurement, where you have the scintillator fiber coming straight out with as little of the fiber irradiated as possible, and then a maximum fiber configuration measurement where you would wrap the fiber around in this channel in order to have more fiber in the beam. The idea is that you're keeping the dose to the scintillator constant and changing only the Cherenkov level. And then in our optical detection, we look at the signal in the blue channel compared with the signal in the green channel in those two configurations. And from the difference in the blue channel divided by the difference in the green channel, when only that Cherenkov changes, we can create this Cherenkov light ratio correction. And with that correction, we can then account for the stem effect, the Cherenkov, in subsequent measurements by subtracting a certain amount based on the signal in the green channel from that blue channel signal. If you're doing a dose conversion for output measurements or something like that, then that's basically just a gain factor that's applied to the whole, that calculated value to convert units from the charge that's measured to dose. So if you wanted to do a dose calibration, you would just give it a known dose in a reference field size, and then the system can calculate that correction or that gain factor. So the W2 has a dedicated electronics box called the MaxSD. This combines both the optical signal detection as well as the signal processing electronics to be able to do the Cherenkov correction. You can do point measurements directly with this device, as well as, of course, your Cherenkov characterization. It does a very fast Cherenkov correction. It's performed for every 10 milliseconds of integration of the signal, so that can then be converted into an analog output that could be sent to your water tank for scanning. So if we look at a little bit of that setup, I have probably better pictures here. I guess it's the same for the Max. If you would want to do your CLR measurements sometime prior to scanning, it doesn't have to be day of. It holds for a while. It's pretty stable. But you would have that minimum fiber configuration, maximum fiber configuration. And then for scanning, there's actually an adapter sleeve that lets it fit any chamber holder. This is our Dose V3D tank, but any chamber holder that will hold a scanning chamber with either a 7 millimeter or an 8 millimeter diameter stem. So you can use it with any other water tank, not just ours. The optical fiber here is then plugged into the MaxSD, which does that Cherenkov correction. And then there's a triaxial output. You just put the MaxSD on the couch next to your scanning tank electrometer, connect the MaxSD output, the triaxial analog output, to the input channel from your water tank. And from the water tank's perspective, it just looks like a diode. You're not applying bias to it, but when the radiation is turned on, a current is received by the water tank. And in that way, you can scan with it very easily with your water tank. You do have to scan slowly because this is a low signal device and because we're trying to make sure that we get good quality measurements to overcome that low SNR. We recommend that you do at least a 1 second dwell at each of the measurement points. This is totally worth it for those small fields. It does become a burden, obviously, if you start thinking about the time it would take to scan larger fields with this sort of detector. But really, that's not the point, right? This is your small field characterization. That's the reason for going down to these small sizes, as well as really needing the water equivalents. So strengths, I guess I didn't show it, but the TRS 483 publication lists KQ values for a lot of different detectors for small field measurements. And the only detector in that entire publication that has unity correction for every field size, every energy of every table it shows up in is the W1. So that beam quality correction factor of 1 is a huge strength for the W2. Water equivalency for both the photons and electrons. It has not shown dose rate or energy dependencies. It has a negligible temperature dependence, so as long as all of your measurements are at room temperature, that shouldn't affect you at all. It's about 0.1% per degree Celsius. If at some point we get FDA cleared to do on-patient measurements, that sort of thing, then there may need to be a temperature correction. But just for QA measurements at room temperature, that's not needed. Obviously, a very small spot size, especially for that 1 by 1 millimeter detector. Sorry for the pop-ups. I meant to turn those off. And then it is MR compatible. We make slightly longer fibers for MR Linacs in order to make sure that the max SD is outside the 5 Gauss line, but there is no metal, no ferrous material whatsoever in this optical fiber. Limitations of the of the scintillator is that because it's not an absolute dosimeter, you do have to recalibrate it occasionally. There is about a 2% decrease in signal for every kilogray of dose that the fiber receives, and so your signal does decrease over time. And you can account for that with the recharacterization, recalibration, but it does require that. Another limitation that we've found is actually that optical signal measurements are slightly non-intuitive to a lot of users. It's not the troubleshooting that you're used to doing with an ionization chamber, the behavior that you're used to seeing with an ionization chamber. So sometimes when things, especially as you're just getting used to using it, trying to figure out what might be going wrong with your setup or your Cherenkov correction, something like that, takes a little bit more troubleshooting than you would be used to with your ion chamber. Once you're used to it, it's actually extremely easy to use. And then I did mention the low SNR means that your scans are a little bit slower. There's a question about the CLR for scanning, actually. Do you need to have a CLR for scanning? Profiles are a ratio output. You do, because as you change your field size for scanning, your output from the W2 will change slightly because the amount of stem that's in the field will change. And so really it is best to take care of that stem effect right at the front, and know that it's taken care of, and that the signal that you're measuring is actually just the scintillation signal and not an integration of additional signal along the stem of the chamber, or of the scintillator, sorry. Great question though. So here's an example of a scan. This was from a publication by Paulina Galavis at NYU Langone. And this is just a 1 by 1 field measured in water compared with radiochromic film. And you can see excellent agreement all the way across. It was pretty exciting when we got these. Kind of the proof's in the pudding. So we're here to help you. That's about all I had for slides. Thank you so much for your attention today. Let me know if you have any questions, either here in the chat or follow up with us for more information or answers to your questions, either on our website, standardimaging.com, or contact us at sales@standardimaging.com. We'd love to talk to you about it more. So thank you once again. Let's see, I see another question. Is a reference detector needed or advised during scanning for the scintillator? Because you're scanning so slowly, you really don't have to have a reference detector. You certainly can if you'd like. I know some systems don't really allow you to scan without, but a single pulse on one end or the other doesn't affect the overall signal magnitude nearly as much as it does in your really short measurements when you're scanning quickly. So no, you do not have to have a reference detector when you're scanning with the scintillator. And then is there a limited lifespan of the scintillator? Yes, theoretically. I'm not sure I know of anybody who's completely dosed it out yet. We usually recommend that you would replace your fiber once the signal goes down below about 80% of the original signal. And really the reason for that is just to protect you from that low SNR causing frustration and causing issues with your measurement, just with the increased uncertainty. Because as your signal decreases, the proportion of Cherenkov or the proportion of the total signal that you're having to remove as you remove the Cherenkov goes up, and so at some point it's a high enough proportion of the total signal that just that act of subtracting the value creates uncertainty in your final measurement. So it's best to replace it at about 80%. Do you really need a CLR correction for scanning in small fields smaller than 2 centimeter diameter? I would recommend it. I guess I have not. I've not tried scanning without that. It's a kind of an interesting question, though. I might have to do some research and figure that out. Maybe contact me afterwards, and we can talk about testing that. Next question: is it suitable? Whoops, I just lost it. There we go. Suitable for dosimetry of proton beams. Our detector has not been tested in proton beams yet. I know there is some research into that down at MD Anderson with some of their homemade scintillators, the benchtop research units. I believe there is a quenching effect in the protons that needs to be accounted for, but it's not something that we have really investigated with the W2 yet. Do we find any volume averaging, especially with cones? With the 1x3, you will need to be cognizant of that for sure. With the 1x1, it's small enough that the volume averaging is minimal. I would advise you to keep an eye on those profiles, though. Sometimes it's nice to confirm with film if you're really down in the couple millimeter size fields. You don't have a flat region in that field, but the 1 millimeter integration is going to be a 1 millimeter integration. It's not a true point. So we can get you extremely close. And with anything, I would say 4 or 5 millimeter size field or larger, it's quite minimal. And you wouldn't have to worry about it very much, but it would be something just to keep in mind, especially as you push the envelope and try and go down to the extremely small fields. Do we provide a loaner for trial? We have occasionally for research projects provided loaners, but that's usually something that we don't do with the W2. But we could certainly, I would say, contact your sales representative and make your case. Why do you need a loaner? And let us know. If you want to talk to somebody who's used it and learn about their experience of it, I'm sure sales can help you. I can help you contact somebody as well. Are there comparisons of the W2 versus a synthetic diamond? I believe there's publication comparing the W1 with a diamond, and the W1 did outperform the diamond. I believe the diamond detector is also listed in TRS 483, so you can look at that for comparison of correction factors as well. You say you're seeing a disagreement beyond the penumbra. Is that with the diamond detector or with the W2? Sorry, I'm not sure I understand that one. I can see it happening with the diamond detector. So the W2 and the diamond are disagreeing beyond the penumbra. Is that what I'm understanding? Yeah, that's a good question. I believe that there is a little bit of energy dependence with the diamond that may be causing you some issues beyond the penumbra. The other thing to be aware of with the W2 is make sure that you're zeroing it before you scan with it. You have to zero your scanning electrometer as well as the max SD. Otherwise, if you've got some background signal, it basically causes your low signal measurements to look higher than they actually are, because you start bumping up against that noise floor or against that background signal that hasn't been zeroed out if you're not zeroing your max SD and your scanning tank. So that's the first thing I would check is your zeroing. But then also look at TRS-43 for the diamond. I'm sure you have already, but I don't recall just at what point field size or energy wise it starts to show some of those effects. Great questions though. Thanks so much. This is a fun discussion. If there are any other questions, I can certainly hang around a little bit more. Otherwise, thank you everyone for the wonderful questions, for your attention today. Thanks for joining me, and I'm looking forward to further discussions about the W2 or small field scanning in general. It doesn't necessarily have to be the scintillator specifically.